everyone. So this is going to be the very last type of angular projectile motion called angular projectile. Now, what this is that it's basically a combination of both horizontal projectile and vertical projectile, all at the same time. So we're going to end up having to do a little bit of both of what we did before. Now, basically, if you remember, vertical projectiles, the ball was given only a velocity, initial velocity, in the vertical direction. And the horizontal projectiles, it was only given a velocity in the horizontal direction initially. Here, it's going to be given a little bit of velocity in both the vertical and horizontal, the y and x-axis. Basically, it ends up getting shot at an angle, hence the term angular projectile. So these are things like hitting a golf ball, hitting a baseball, kicking a football or a soccer, Angry Birds. All of these are examples of angular projectiles. Now, once again, when we have these objects undergoing angular projectiles, we still only have acceleration in the y direction caused by gravity. So, just like what we did before with the horizontal projectiles, the acceleration is always going to be 0 in the x, 9.8 or 10 meters per second squared in the y direction. But because we're going to have an object moving initially straight up, we're going to have to make sure that it's a negative 9.8. Here, another thing to note, just in case they ask, the path that the ball always takes is parabolic, or it follows a parabolic shape. And that's because of the fact of the velocity and the acceleration only acting downward. Uh, just like before, you can always tell based off the wording whether this is an angular projectile question. For example, they'll give you a question like this where they strictly tell you an angle, hence, again, angular projectile. Or, as I said before, they'll give you velocity in both the vertical and horizontal direction, something like this. These questions are going to be pretty much the easier ones because you can just jump straight into making the chart. But when you're given a question that looks like this, you're going to have to do one step before you can actually start making your chart. Yeah, so again, the main thing is that there's going to be an initial velocity in both the x and y direction. So if you're given an angle, just like what we did before, the moment you see an angle, you have to immediately take that velocity and break it up into its components. Again, half the time they're probably going to give you the components and you just kind of put it straight in there. But other times, especially with free response questions, they're going to give you it with an angle and you need to make sure you immediately break it up into components. And then once you do that, that original number never gets used again. You ignore it, erase it, cross it out, do something. Never use those numbers again. You're only using the components. So a good example is here. Let's say they have a ball being kicked with 10 meters per second at a 30-degree angle. We break it up into its x and y components. We get that the vertical velocity using SOHCAHTOA is 5 meters per second and the horizontal is 8.7. When I make my chart, again, I'm ignoring that original 10 and the 30 degrees because I've broken it up into a 5 and 8.7. These numbers are what I can use. This I can't. Just remember, if I'm telling you to do SOHCAHTOA and break up the components, it's because you need to do it. Too many times do I see people go through all the trouble of using SOHCAHTOA, finding the components, and then they put the 10 or the original velocity back into the chart. So don't do it. There's a point, there's a reason to this, so use them. So once we get those velocities, then we can make the chart. All right, so you get an angle before you even continue reading the question, reading what it's asking, or anything like that. Break it up into components because guess what? Half the time, they might even just be asking for a component. So you've already solved a question, you just have to figure out which one you're doing. So again, it's really important that you make sure that you always do SOHCAHTOA the moment you see an angle and then reread the question to figure out all the other information. So again, just like with the horizontal projectile, we're going to have a vertical side and a horizontal side. Now, The interesting thing I said before is that this is a combination of the vertical projectile stuff and the horizontal projectile stuff. And it's actually seen in the chart. The Y side, the vertical side, actually gets treated exactly like we do with the vertical projectiles. If you remember with the vertical projectiles, it was that whole thing of D was zero if they said lands at the same height, and VF is zero if they say max height. Same thing applies here. The X side, the horizontal side, gets treated just like you did in the horizontal projectile, where it's moving at a constant velocity and you can only use it if you're only missing one piece of information. Most of the time, like before, you're pretty much mainly going to focus on the Y side, and the X gets used basically near the end. So once again, something in the Y is zero. In fact, one thing that could definitely be helpful to remember is that something in each column will always be zero. We know that in the X column, the acceleration is zero. In the Y column, one of these terms is going to be zero depending on what we use as what they ask for. If they ask for the total time, saying that it lands at the same height, anything like that, then we know that the D or the displacement is going to be zero. And if they say the phrase max height, then the final velocity is going to be zero. Now, here's the one weird thing that you have to be careful of. You need to make sure that the times for these two columns make sense. There are going to be very few times, not super common, but it comes up every now and then where when they talk about the Y values, they give you information for going to its max height. And then in the X column, they'll talk about it going up and down and landing. If you're doing something like this, where it's going only to max height, you have to remember that the time in this column when you use max height only gives you half of the time because you're only looking at half of the picture. But over here, if they say something about wanting to know where it lands, you have to recognize that this requires the full time. So what I usually do when I make my chart is I actually make sure to put a line down here. I said I didn't really do that when I made the charts for the horizontal projectiles, but here I do because it's not always going to be the case where these times are going to be the same, because this might be referring to only half of the path while this refers to the full path. All right, again, you'll see it in the wording, but you just want to be careful with that time. And you want to remember that depending on what information they give you or what they're looking at, again, total time versus max height, landing versus max height, changes what time you end up finding with those numbers. And once again, with the velocities, once we have the horizontal velocity, initially we have the final velocity. I said here that only the total time's the same, but there had been a few questions where they wanted to know how far it moved to max height, but it's an extremely rare time. 9 times out of 10, when they want you using this X column, it's for the full time, full distance it lands. And this just goes back to what I said before about how you can only use the X side if you're only missing one number. And if you have more than one piece missing, you have to use the Y side. All right. So here's the first question. Pause video working itself, and we'll go over in a second. All right. So the direction of the ball's velocity at point X. So point X, it's at the very top of its path. Vertically, at the maximum height, it has no velocity. But horizontally, it's always going to have a constant horizontal velocity. So it ends up having a velocity directed east. So vertically, it got to zero, but horizontally, you still have that initial velocity. Okay, here's the next question. Pause the video working itself. I'll go over in a second. All right, so the direction of the ball's acceleration, just like always, the ball's acceleration is always going to be down. Gravity always acts down on an object no matter where it is in its path, and it never changes. The acceleration is down. Here's the first calculation question. Pause video work and stuff. We'll go over in a second. All right. So right here, the first thing I do, I see the 44 meters per second at an angle of 37 degrees. I'm going to use SOHCAHTOA. Uh, you could do SOHCAHTOA. Another thing you could do is if you look on the back of your reference table, you should see these two equations, a sine theta and ax sine theta. Oh, sorry, cosine theta. These are going to be your components, the y component and the x component. So for the vertical component, I'm going to do ay 44 times sine of 37 degrees. And when I do that, I end up getting 26.5 meters per second. I could do the same thing, and I probably should do it for the horizontal side. 44 cosine of 37 degrees. Unfortunately, I don't have a calculator on me, so I won't be able to figure that out. But if I did have it, I would put it straight into the chart right there. All right, so whatever you get when you do this gets put in right there. And again, the 44 is now removed. So cross it out, if you will, so you don't remember or forget to ignore it. All right, part B, the maximum height reached by the softball. So once I have this, now I actually want to start plugging in my numbers. So again, I know what my acceleration is, it's 0. I know what it is in the y direction, -10 or -9.8. They say the phrase max height. So I know my final velocity is going to be 0. And my displacement is what I'm looking for. Now I'm going to actually do this. I'm going to draw this to remind myself that this is all just a half of the path, that I'm going from the bottom to the maximum height. This is going to play a part later. So once I do this, d vi vfa, I'm going to use the timeless equation, vf squared equals vi squared plus 2at. I'm going to drop my units for now, 26.5 plus 2 times -10d. Solving this, and I end up getting that the maximum height is going to be 36 meters, about. So 36 meters. All right. Now, for part C, there's two different ways I could go about doing this. Now, if this was a free response question, I would recommend remaking the chart, because if you make a chart for part B, let's say, like we did here, that chart does not carry over to part C. You would have to redo it if you want to get the credit for the units. If you were instead just going to leave units in the substitution, you wouldn't have to carry over the chart. But if you're using this chart to kind of get around the whole plugging in units like I did here, it has to be redone in the next part. So you could redo it. This would still be 0. This would be -10. This would be 26.5 still. The only difference now is because it says total time it's in the air. That means it's landing, it's coming back to the ground. My displacement now becomes 0. And this is what I look for. So I have dviat. I could use the magic D. D equals VIT plus 1/2 AT squared. 0 equals 26.5t minus 5t squared. Remember, when it comes to the test time, this would not be acceptable. You would have to write plus 1/2 times -10 times t squared. I'm just, I'm using a mouse, so I'm allowed to do that. I have a t here and a t here, so I'm going to divide it out. So now I have 0 equals 26.5 minus 5t. Add the 5t over. do 26.5 divided by 5, and you end up getting that the total time it's in the air is 5.4 seconds. And that's it. Now, you could have also done was this, and this is why I said that I'm going to put this up here to remind myself what it's looking at. So I could actually use these numbers and maybe VF, VI, AT, maybe use the acceleration equation, plugging my numbers in, getting 26.5 equals, 0 equals 26.5 minus 10t, getting that the time is 2.7 about, and then realizing that this isn't my total time, this is only half of the time. Then you could just double this and you would get the 5.4. So again, you don't always have to double the chart or redo the chart, but I only recommend it if you make sure to make these precautions of reminding yourself this is only looking at half of the time. Maybe even writing that this is half time down here to remind yourself, that if you're looking for total time, to double it at the end. All right. So whichever method you like, go with it. But again, I recommend redoing the whole thing until you get a good handle on this material. Here's the next question. Pause video work on itself, and we'll go over in a second. All right. So here we have a projectile being launched compared to the vertical component of the velocity of the initial velocity of the projectile. The vertical component of blah 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 when it reaches its max height is, the answer is less, because at the initial velocity, it doesn't matter what it was, it's going to be some number. So 5, let's say. But at max height, the vertical velocity is always 0. So no matter what the initial velocity was, the initial velocity is always going to be higher than this. So the vertical component when it reaches the max height is less compared to the component initially. All right, 41. Pause the video work on itself, and we'll go over in a second. All right, so they give us an angle, but they don't tell us any speeds, and that's the important thing. We don't know the speeds. So what I'm actually going to do is start plugging in numbers into this chart. So we know that the ball lands 700 meters away. We know that the acceleration is 0 and negative 10. It says lands 10 seconds after it's fired. And again, this is full time. All right. Now, normally I've said that you can only be missing one thing in the X, but you have to remember that VI and VF are the same thing, always the same. So this is enough information. What I can do is use the magic D. D equals VIT plus 1/2 AT squared. 700 meters equals VI times 10 plus 0. Remember, we're only using the X side. And you end up getting that the initial velocity was 70 meters per second. So I could plug that into here. And that's it. Now here, they want the vertical component of the initial velocity. There's a few ways I could go about doing it. I think the easiest thing is just to make a triangle. So the 70 is this number right here. And I don't know what this number is, but that's what I'm looking for. I also know that this angle is 35 degrees. So going back to basics, I have an opposite and an adjacent. So I'm going to use tan theta is opposite over adjacent. So tan of 35 equals y times 70. And you should end up getting about 50 meters per second. All right. I think this might have to be the last question. So pause the video, work on itself, and we'll go over in a second. All right. So once again, the moment I see this angle and I see that I have a velocity, meters per second, I'm going to do SOHCAHTOA. So AY, A sine theta. So this will be 5 times sine of 30. So AY is going to end up giving me 2.5 meters per second. So I'm going to put that number here in the Y column. Then I also can do AX is 5 cosine 30. And I get that this is going to be 4.37 meters per second. And that's going to go here, 4.37. I could put it here in the final because I know the acceleration's 0 and negative 10. Once again, I do not care about the 5 and the 30 anymore. Once I break it into components, that's all I care about. Otherwise, I wouldn't have done it. Now I'm going into the question. What is the maximum height reached by the football? Well, once again, maximum height. So this is only looking at half time. Max height looks for D, which means VF is going to be 0. Timeless equation. You should probably notice by now that the timeless equation almost always gets used whenever they say max height. When we get to the energy topic, you'll see why. So plugging in my numbers, plus 2 times negative 10 times D, we get that the max height reached by the ball is 0.32 meters. So not that high, 32 meters. Sorry, 32 centimeters. All right. Now, again, total time the ball is in the air. I could repeat these, repeat the chart, this time changing what is going to be 0 in the Y column because it's total time it's in the air and it's going to end up falling. This ends up being 0, and now this is going to find full time. Use timeless equation. Zero, 2.5t minus 5t. Remember, you're not allowed to get away with this. But solving this, I end up getting 5t equals 2.5. So this ends up telling me that the time is going to be about 0.5 seconds. Once again, you could have used these numbers, found that the time using these numbers gets you 0.25 seconds, and then doubling that to figure out that the total time is 0.5. Once we have that, how far from the ball player does the ball land? They're looking for this horizontal distance, again, for the full amount of time. So we're going to use the magic D again. This time it's going to end up being D equals 4.37 times 0.5 plus 0, because again, we're only using the x acceleration. And we get that the ball lands 2.21 meters away. All right, and that's it. I'm going to post another video about this where we go over some more questions, and that will be the last one about this. If you have any questions, please let me know. Send me a message to remind or join Extra Help. Otherwise, good luck, and I'll see you later.